Okay, so we're on page 523 in your workbook, your Absolute Value Workbook for Math 20, Lesson 4, and looking at solving quadratic inequalities in two variables. So just a quick review of what we looked at previously was solving linear inequalities in two variables, and we recognized that our graph divided our Cartesian plane into two sections, and one of which satisfied the inequality and the other side which didn't, and we decided that through using test points by substitution. In terms of graphing, we would graph it as if it were an equation, and then it would be a solid line if y was greater than or equal to or less than or equal to, and it would be a dotted line if it was just a greater than or less than, indicating that the graph itself was not going to satisfy that inequality. So let's take a look at our quadratics then. It's exactly the same premise that we looked at with linear inequalities in two variables. So again, we've got our two variables, and in this case we've got the quadratic as well, and so it says explain why the point 3, 0 is in the solution region of y greater than or equal to x squared minus 3x minus 4. So it already tells us that it is, but to prove that we simply just do that substitution. So y is 0, so 0 is greater than or equal to 3 squared minus 3 times 3 minus 4, and we're just going to simplify that right side as if it was an order of operations expression. So we've got 9 minus 9 minus 4, so 9 minus 9 is of course 0, minus 4 is just negative 4. So 0 is greater than or equal to negative 4, and of course it is greater than, so it satisfies. So left side is in fact greater than or equal to the right side, so the point satisfies the inequality, which means that it is part of the solution region. Okay, so again, solution region, meaning that it's a whole bunch of infinite number of points that will work and satisfy, as opposed to an equation where we're looking at only one possible solution. So taking a look at part B then, it says determine whether the following points are either in y is greater than or equal to x squared minus 3x minus 4, or y less than or equal to x squared minus 3x minus 4. And so you're going to test all of these points out. And so then that is through substitution. And so go ahead and just press pause on this and work through all of those points, and we'll come back and talk about that when you're done. So the strategy that you probably had was substituting the points in to one of the inequalities, and if it worked, you put it within that solution region, and if it didn't work, my guess is lots of you just put it into the other solution region, assuming that if it didn't work in one, that it would automatically work in the other, and if it worked in the one, that it wouldn't work in the other. Based on the points that they gave and based on the inequalities that they used, that would in fact be true. The one point that I actually wish that they included, and I'm just going to add that in right now, is I wish they actually also included the point 0, negative 4. And why that particular point? It could have been any number of points, but that one specifically is, if you go ahead and try that in both inequalities, what you would find is the left side is of course negative 4, because that's just y, and the right side with x equal to 0 is going to be negative 4. So in fact it is equal to, left side equals to the right side, so in fact with that point it satisfies both. inequalities. And so I think I just wanted to bring that up because it's important to recognize that, especially if it's a greater than or equal to, less than or equal to, that if it was right on the graph, as it is in both cases here, then what we find is that lies on the graph, and therefore it is true for both cases. If they just had y greater than and y less than and not equal to, then that particular point actually wouldn't satisfy either of the graphs. So the assumption of it just being either black or white, just A or B, doesn't actually allow for this possibility. So just keep that in mind if that was to come up in a future question. Okay, so hopefully you've got the same answers as I did with the other 4 points. So they've given us, they had that one in the beginning, 3, 0, which did satisfy it, and then out of the 10 remaining points, 4 of them joined that 3, 0, and the other 6 were in the other one. So the diagrams below show the graph with the equation y equals x squared minus 3x minus 4. And so if we plot all of the points from the top row into the first grid, then we've got 3, 0 and 0, 0, the origin, and 0, 3 and 1, 4 and 2, negative 2 and 0, negative 4, which I added in, and these points are all within that solution region, so they all satisfy it. So that confirms that it is everything that is inside that quadratic. And remember, these arrows indicate that that graph goes up and up into forever, and so it is truly separating our coordinate plane into 2 separate areas then. Okay, so similar if we plot the other points, so negative 3, 0, 0, negative 7, 7, negative 1, whoops, there we go, and negative 4, and 2, and 8, and 5, negative 5, negative 2, and again that 0, negative 4. Those all satisfy y less than or equal to x squared minus 3x minus 4. So then our solution region is everything outside of that quadratic. So we would just shade all of that in then. Okay, and so that's what we just did for part D right there. Awesome. So let's take a look then, and the procedure that it goes through is essentially the same thing that we did with linear, which is to draw the graph of the quadratic equation, either using the intercepts or other means. Other means, of course, would be using vertex form. So perhaps bringing back fond memories of completing the square so that we know where our vertex is, and then drawing in our quadratic with some semblance of accuracy, please, and the graph will then be solid or broken depending on whether the inequality includes the equal to or not. Okay, and then pick test points. Again, my strong suggestion would be not just one test point, but pick one inside, pick one outside, and one should work, the other should not work. So it also just helps to potentially double check your math as well. Sometimes if somebody picks one which they think is inside and outside, if they both work, then either something's wrong with your math or perhaps it was an error with your graph. Okay, so let's take a look then. So shade the solution region to the inequality y less than 20 plus x minus x squared on the grid below. And so we have nothing. And again, assuming that you don't have your graphing calculator to give you any of the information, so you have to go back to, well, how is it that I'm going to graph this? So a few things that we can do. So first off, so some information. Consider then the actual quadratic itself, which is y equals 20 plus x minus x squared. So if we were to say factor that, then if we factor, we've got x and negative x, and so then that is going to be 4 and so 4 plus x and 5 minus x, and I'll just do a quick check with FOIL in my head, multiplying those two binomials together, and it does in fact work. And so that tells me that if we're solving that quadratic equation, so if y equals 0, then our x-intercepts, so when y equals 0, then either 4 plus x equals 0, so that would mean that x is equal to negative 4, or 5 minus x equals 0, which means that x equals 5. So we know our x-intercepts, and so we've got our negative 4 right here. And we've also got our positive 5. Let's place that right here. Other little hints for us as well. We know that our a value, so the coefficient for the x squared, is negative, which means that it opens down. And we know that our y-intercept, so if we substitute in x equals 0, our y-intercept is then going to be 20. So we're looking at this right here. And then the issue, though, for us, so I get a sense of what the shape of the graph is going to be, and I'm actually, just for the interest of kind of scaling a little bit, so if this is actually 20, then my negative 4 might be more like this. Positive 5, something more like this. So we know already that the graph is going to have this shape. The vertex is going to be above this, so it comes a little bit higher than that 20 and continues down like so. I've done it as a dotted line and not a solid line because it's just less than, it's not less than or equal to. If we wanted to be more precise than that, then we would need to complete the square with that to know exactly what our vertex is. So, or we could do it in a second way as well. So because we know our x-intercepts and it happens to be nice integer values, you know that our quadratics are going to be symmetrical, which means that our vertex happens halfway between, or at the midpoint of our two x-intercepts. So halfway between negative 4 and positive 5 is going to be 1/2. So our p-value, we know our p-value is going to be 1/2, or the x-value of the vertex is 1/2. So you could actually just substitute in 1/2 in for the x to figure out what that y-value is. And let's just also just do a quick review on how to complete the square as well. But first off, let's do it this way. So if I know that midpoint is 1/2, so then for my vertex, we know that x is equal to 1/2, so then y will equal to 20 plus 1/2 minus 1/2, which is squared. So then that is 20 plus 1/2 minus 1/2 squared, so minus 1/4. Whoops. And so then that would give us 20 1/4, or you could think of it as 81 quarters. Other people might think of it as 20.25. Either way works. Not sure why I put closing bracket there. Okay, so certainly because I put 1/2 in here, it would be good to continue with a fraction form. So I'll write in 81 quarters for that. Okay, so that's the way, just by if we had some nice values for our x-intercepts, that we can just then find that midpoint value where the middle is, and then substitute that in to then find the corresponding y-coordinate. Alternatively, we could also complete the square. So let's just find some space to do that, and I'll just change the color for us. So let's start. So if we've got y is equal to, and I'm just going to rearrange it so that it is negative x squared plus x plus 20. And so if you recall, our vertex form is y is equal to a times x minus p all squared plus q. So that's why I want to just rearrange it so that it is in descending order. So at this point we need to factor out our a value, which is the -1. So we've got negative, then x squared minus x, and I'm going to leave that plus 20 hanging outside because that is part of my q value, and then we need to complete this square so that this is a perfect square. And this one's unfortunately not very pretty, and we already know that it's not going to be pretty because we know our vertex is fractions. And so we're going to then take that middle term right here, that -1, which is the coefficient of our x. So I'll just come over to the side here, -1, and we're going to divide it by 2, and then we are going to square that. And so when we square that, that is equal to 1/4. So that means that I need to add 1/4, but because I'm adding 1/4, I also need to subtract 1/4 since I want that value to end up being exactly the same as the previous value. Okay, and so then from here we've got negative and x squared minus x plus 1/4. That is my perfect square trinomial. And so we'll factor that, so that gives us x minus 1/2 all squared, and that -1/4 is going to get kicked out of the brackets, and in order to kick it out of the brackets I need to multiply it by that a value. So -1 times -1/4 is +1/4, and then plus the 20. And so then that's where we get negative and x minus 1/2 all squared plus, and 1/4 plus 20 is that 20.25 or 81/4 then. So that is our vertex form. So that emphasizes the a value being -1, meaning that it opens down, and p is our corresponding x value for our vertex, and q 81/4. So and there we have it. So that's our vertex form based on completing the square. So 2 ways to find the vertex if you're looking for some accuracy, and of course you guys know that I am and always will be looking for that accuracy when it comes to sketching in your quadratics then as well. When it comes to then shading, so back to that inequality, so we've got the quadratic graph. We know that it's a dotted line because it's less than, so now we need to pick some test points. So again, the obvious one in this particular case is going to be to pick the origin, so 0, 0, because the quadratic does not go through the origin. The other point that I'm going to pick to make life easier for us, since you have to add x and subtract x squared, then picking a value where x is equal to 0 is going to be really nice. So yeah, sure, could you pick something out here? Absolutely. X is 7 and y is, pick something else. Absolutely. Could you pick x is 6 and y is 0? Definitely. But if we know for sure that the y-intercept is 20, if I pick, say, y is equal to 21 or 22, then x is 0 at that point, so that makes that really, really easy for us to substitute in. So our first test point then is going to be 0, 0, and if we test that in, and we test it in our original inequality, so we've got 0 is less than 20 plus 0 minus 0, minus 0 squared, and is 20 less, or 0 less than 20? It absolutely is. So that tells us that this is part of our solution set. So that means that I am shading everything inside that quadratic. And just to double check though, we'll test as well. We had picked x is 0, y is 20, let's say 22. So if we check that, in our original inequality, the left side is 22, and that's supposed to be less than 20 plus 0 minus 0 squared, so 22 less than 20. That is absolutely false, of course, which tells us that point is not part of our solution region, does not satisfy our inequality. Okay, awesome. That's it. So please let me know if you guys have any particular questions. Thank you.